In this series of 2 videos, we take a look at chapter 8.4, which covers complex vector spaces. Our learning objectives for these 2 videos are to recognize and perform vector operations in complex vector spaces, which we denote CN. So like how we had the n-dimensional real numbers, we have the n-dimensional complex numbers. My font is kind of small on here, so let me write this just a touch bigger over here so you can see. Sometimes we write it with fancy C. You could also just put capital C to the end. So that's what this right here is denoting. So just like the n-dimensional real numbers, but now we're thinking about n-dimensional complex numbers. And remember, complex numbers are in this form, real plus imaginary part, where the real part is just a real number A, and the imaginary part is a real number B multiplied by the imaginary number I. We are going to see how to represent a vector in this complex vector space by a basis. We're going to see how to find the Euclidean inner product, the Euclidean norm, and the Euclidean distance formula in the complex vector space of CN. And we're going to see how to recognize and check complex inner product spaces. So let's start with the definition of what is a complex vector space. So a complex vector space is one in which the scalars are complex numbers. So if V1 through Vm are vectors in a complex vector space, then a linear combination is of the form C1V1 plus C2V2 through adding CMVM. And you can ignore the little red underline part here. That's just from my word processor when I type this. It underlined it like it's a spelling mistake. And so in this case, the scalars C1, C2 through Cm are complex numbers, not real numbers. So we are still thinking of the vectors as linear combinations in this complex vector space. The big difference is that our coefficients are complex numbers. So let's take a look at an example. We're going to let V be the vector 1 plus 2i in the first component and 3 minus I in the second component. And U be the vector negative 2 plus I in the first component and 4 in the second component. These are vectors in a complex vector space V2. So you could denote that C with a 2. That's what this says here. It just is kind of hard to see. And so we are going to perform all these operations. We're going to add V plus U. We're going to take 2 plus I and multiply it by V. And then we're going to calculate 3V minus the quantity 5 minus I multiplied by U. So the easiest way to do these calculations for V plus U are in column matrix form. You could also just do it component by component. But if we write V as a column matrix with the first entry in the first row and the second entry in the second row and do the same for U, we see if we add them up component by component, we get negative 1 plus 3i for the first component and 7 minus I for the second component. So when you're adding or subtracting vectors, you just do component-wise complex addition or subtraction where you combine the real parts and the imaginary parts. Problem B here is to multiply 2 plus I times vector V. So we multiply down here 2 plus I times the first component of V, and you can expand it down so that you'll get 5I. So you follow usual factoring through this. And then we're going to multiply 2 plus I times 3 minus I, the second component of V. And if you factor through and combine like terms, you get 7 plus I. So altogether, 2 plus I multiplied by V gives us 5I in the first entry from this first calculation and 7 plus I in the second entry from the second calculation. The next calculation, part C, is 3V minus the quantity 5 minus I multiplied by vector U. So the first thing we do is we take that 3 and we distribute it through vector V here. So you can see that just triples each value in each component of vector V. And then we take 5 minus I and multiply it by U over here. And so again, we're going to distribute that through and the first term and the second term. And so we get term here. And then combining like terms, we get 12 minus I in the first component and negative 11 plus I in the second component. So a lot of arithmetic in these calculations, and it works just like you would expect and what you know from combining complex numbers. So let's take a look at a standard basis for a complex vector space. So many of the properties of our n-dimensional real numbers are shared by the n-dimensional complex numbers. So for example, the scalar multiplicative identity in the n-dimensional complex numbers is the scalar 1, and the additive identity in the n-dimensional complex numbers is the 0 vector, which is just 0 in n dimensions. And the standard basis for the n-dimensional complex numbers is the same standard basis for Rn, so E1 through En, where that 1 is in the nth position or the ith position if you rotate from I going from 1 to n, and the other entries are all 0 in the standard basis. And just like as we know for Rn, you can construct any vector in Cn using this standard basis. And in Cn, the big difference is that our coefficients are complex numbers. So let's take a look at another example. In this example, we're going to verify basis. So we're going to show that this alternate basis, I00 is the first entry, II0 is the second entry, and 00I is the third entry, is a basis for C3. So that's the three-dimensional complex numbers. So the dimension of C3 is 3. So the set V1, V2, V3 is a basis for C3 when it's a linearly independent set. So to check for linear independence, we're going to set the linear combination of vectors in S equal to 0 as we did below. So we're going to use our coefficients here, C1, C2, Z3. So you can see we're just distributing the C1, the C2, and the C3 through to each component. In this case, they're each of the i's. And then combining like terms, we've got C1 plus C2 multiplied by I in the first component, C2 multiplied by I in the second component, and C3 multiplied by I in the third component. We set this equal to 0. So using what we know that obviously I is non-zero, then it must be that C1 plus C2 is 0, C2I is 0, and C3I is 0 tells us C2 and C3 must also be 0. So since C2 and C3 are 0, that forces C1 to also be 0 because C1 plus C2 has to be 0. So that tells us each of the C's, C1, C2, C3 are 0. And so our set V1, V2, V3 is linearly independent. So let's talk about the space of complex valued functions. So consider a set of complex value functions in the form of f of x equals f1 of x, the real part, plus I times f2 of x, where I multiplied by this real valued f2 of x is the complex part of the complex valued functions. So f1 and f2 are real valued functions of a real variable. And then the I in here gives us the complex part in the second term. So we're going to let the set of complex numbers be the scalars for S. So vector addition is calculated like this. F of x plus g of x is going to be f1 of x plus I f2 of x plus g1 of x plus I g2 of x. And then combining the real and the imaginary parts, we get f1 of x plus g1 of x, that's the real part, plus I multiplied by f2 of x plus g2 of x, the complex part in the second term here. So it can be shown that for S, scalar multiplication and vector addition form a complex vector space. So for example, to show that S is closed under scalar multiplication, let C be A plus BI, a generic complex number. Then if we multiply C by f of x, changing it to A plus BI times f1 of x plus I f2 of x, distributing through, we see we can distribute through and then recombine to get A f1 of x minus B f2 of x is our real part, plus I B f1 of x plus A f2 of x quantity as our complex part. So we've got the real part and the complex part. So this is closed under scalar multiplication as well. So the set of complex valued functions is an example of another complex vector space. In the next video, we're going to see how we define what's known as Euclidean inner product and do some inner product calculations in the complex vector spaces.